I'd like to take a look at a few more integration by parts problems. This integral over here is a classic type 3 problem. You can apply integration by parts twice to this integral, and you can get the original integral to reappear on the other side of the equation, but with a minus sign in front of it. And you can let u equal to e to the x, or you can let u equal to cosine x. Either one of those choices will work. You sometimes see variations on this integral here, like this one over here, but the basic idea is the same. You can apply integration by parts twice to an integral like this and get the original integral to reappear on the other side of the equation, but with a different coefficient in front of it. And this is a slightly less straightforward type 3 problem, and this is an interesting type 4 problem. I'll take a look at the secant cube problem first. If I wanted to apply integration by parts to this integral, what I might try is letting u equal to secant cube x, and then dv would be equal to dx. So I'd have u is equal to secant cube x and dv is equal to dx. I need to calculate du, so I need to take the derivative of this with respect to x. So I need to use the chain rule, but first I need to use the power rule and differentiate with respect to secant x. So that'll give me 3 times secant x raised to the 3 minus 1, which is 2, times the derivative of secant x with respect to x, which is just secant x tangent x, and all that's times dx. Now I can combine these two secants and get secant cube x, and altogether I'll have 3 secant cube x tangent x dx. Now I need to calculate dv, so I can just integrate both sides of this equation, and on the left I'll have integral of dv, which is just equal to v, and over here I'll have integral of dx, which is just equal to x. Now the integration by parts formula tells you that the original integral is equal to u times v minus the integral of v du. But if I look at the integral of v du, that's going to be equal to x times all this stuff over here, and that's even more complicated than the original integral, so that's not the choice you want. When you do integration by parts, you need to find a dv that you can integrate pretty easily. So what you could do over here is take the secant cube x and split it into secant x times secant square x. And then you can let the dv equal to secant square x dx, and you can integrate that fairly easily. And what's left over will be equal to u. So I'll have u is equal to secant x and dv is equal to secant square x dx. So v is just going to be equal to the integral of secant square x dx, but that's just equal to tangent x, and that's because the derivative of tangent x is equal to secant square x. Remember, if you want the indefinite integral of some function f, that's just defined to be another function that differentiates to that function. So if we want the indefinite integral of secant square x, that'll be tangent x, because the derivative of tangent x with respect to x is equal to secant square x. So v is equal to tangent x. We need to calculate du, so we have to take the derivative of this with respect to x, but the derivative of secant x with respect to x is just equal to secant x tangent x, and all that's times dx. So the integration by parts formula tells you again that the original integral is equal to u times v minus the integral of v du. So u times v is going to be equal to secant x times tangent x, and that's going to be minus the integral of v, which is tangent x, times du, which is all this stuff over here, which is over here. So now what I can do is bring down the secant x, and I can combine these two tan x's and get a tan square x. And what you can do now is you can take this formula here to get something to substitute for tan square x. So you can take this 1, bring it over to the other side, and you'll have tan square x is equal to secant square x minus 1. So you can substitute this for the tan square x. So this term over here will be equal to that. By the way, this formula over here is pretty easy to derive. Since sine square plus cosine square is equal to 1, you can just divide both sides of this equation by cosine square, and that'll give you sine square over cosine square, which is tan square, plus cosine square over cosine square, which is just 1. And over here, 1 over cosine square is just equal to secant square. So this term is equal to this. Now what you can do is just distribute the secant x onto these terms. So you'll have secant x times secant square x is equal to secant cube x, and you'll have secant x times minus 1, which is just minus secant x. So now what you can do is you can put brackets around this integral over here, like this, and you can just let the integral distribute over the two terms inside. So you'll have the integral of secant cube x dx minus the integral of secant x dx. And then you can just distribute this minus sign onto these two terms. So you'll have minus secant cube x dx, and minus times minus is a plus, so you'll have plus secant x. So the original integral has reappeared on the other side of the equation, but with a minus sign in front of it. And altogether you have the original integral, and that's equal to these three terms over here. So now what you can do is you can just take this term, bring it to the other side of the equation, and combine it with the original integral. So you'll have twice the original integral is equal to these two remaining terms, the secant x tangent x plus the integral of secant x dx. Now what you can do is you can multiply that equation by 1/2, and you'll get the original integral is equal to 1/2 this term plus this term. So what you've succeeded in doing at this point is taking the original integral and rewriting that in terms of a simpler integral. And you can just look up the result of this integral, and that's going to be equal to the natural log of the absolute value of secant x plus tangent x plus c. Now I can distribute the 1/2 onto these two terms, so I'll have 1/2 those two terms, and distribute the 1/2 onto the c, so I'll have plus 1/2 c. But 1/2 of an arbitrary constant is still an arbitrary constant, so I can just write that as c. So the original integral will be equal to this. Now I'll take a look at the type 4 problem. I need something that I can integrate pretty easily, so what I could do is I could choose the dv to be equal to e to the x times dx. Then whatever's left over is going to be u, so u is going to be x over x plus 1 square. So I'll have u here and dv equal to e to the x dx. So v is just equal to the integral of both these sides. So the integral of dv is equal to v, and the integral of this side is just the integral of e to the x dx, which is just equal to e to the x. So now I have to calculate du. So I have to take the derivative of this with respect to x. And in order to do that, I can just use the quotient rule, and the result of that is just this term over here, and that's times dx. So the integration by parts formula tells you again that the original integral is equal to u times v minus the integral of v du. But if I look at the integral of v du, that's going to be equal to e to the x times all this stuff over here, and that's even more complicated than the original integral. You still have a factor of x in the numerator, like over here, but in the denominator, this term is cubed now, and it was only square before. So this is not the choice you want. But what you could do over here is you could split up the integrand, so you'd have x times e to the x, and that would be multiplied by 1 over x plus 1 square. So you could let the dv equal to this part, which you can integrate pretty easily, and then what's left over will be equal to u. So you have u equal to x times e to the x, and dv is equal to 1 over x plus 1 squared dx. So in order to get v, I have to integrate this. So how do you integrate this? Well, you could just do a u sub and let u equal to x plus 1 and then apply the power rule. But instead of defining u explicitly, what you could also do would be just to take this term, move it to the top, so it becomes x plus 1 to the minus 2, and take the dx and replace that by d of x plus 1. And the reason you can do that is because the differential distributes. So d of x plus 1 is actually d of x plus d of 1, but d of 1 is just 0. So you haven't changed anything by adding the 1. And the reason the differential distributes is because the derivative distributes. If I wanted the differential of these two terms, that would be equal to the derivative of these two terms times dx. And the derivative of these would just be f prime plus g prime times dx. And I can let the dx distribute, so I have f prime dx, which is just df, plus g prime dx, which is just dg. So you can see that the differential distributes over these terms. So now what you can do is just apply the power rule to this integral over here and use x plus 1 as the variable of integration. So this term is going to become x plus 1 to the minus 2 plus 1, which is x plus 1 to the minus 1, and that's over minus 1. And then you can just bring this to the bottom, so the exponent will become positive, and you'll have x plus 1 over here, and bring the minus sign to the top, so you have minus 1 over x plus 1 for v. Now u is equal to x times e to the x. And this choice, by the way, violates the Lyate rule of thumb, because you have x here, which is algebraic, and you have e to the x, which is exponential, and Lyate doesn't tell you to multiply these different terms together. So anyway, you need du, so you have to take the derivative of this with respect to x. So you could use the product rule. So the derivative of x with respect to x would be 1 times e to the x plus x times the derivative of e to the x with respect to x, which is just e to the x, and all that will be times dx. Then you can just factor out the e to the x, so you'll have 1 plus x times e to the x dx. But if you look at this derivative over here, you'll notice that it's more complicated than the original function. So this is also atypical for an integration by parts problem, because in integration by parts you usually choose u to be something that's simpler after you differentiate it. So the integration by parts formula again tells you that the original integral is equal to u times v minus the integral of v du. So I have u times v, and I'll write the v first, so I have minus 1 over x plus 1, and that's multiplied by x times e to the x, and that's minus the integral of v over here times du, which is all this stuff over here. Now the nice thing about this integral is that this term cancels with this term. So you get this cancellation here between v and du. Now what you can do is take the x times e to the x and multiply it by the minus 1. So you'll have this over here, and that'll be over x plus 1. Then you can take the minus sign here and bring it outside the integral, so you'll have plus the integral of whatever's left over here, which is just e to the x times dx. And then this integral is easy to do, so you can just bring down this term over here, and the integral of e to the x dx is just equal to e to the x plus c. And that's it.